Magnetic field can be detected using a magnetic needle. The lines of magnetic induction of a permanent bar magnet emerge from the North Pole and enter the South Pole. They continue inside the magnet and form closed loops. A conductor with an electric current also creates a magnetic field. Let's consider the magnetic field of a solenoid. Comparing the lines of magnetic induction of a solenoid with those of a permanent bar magnet, we can notice complete similarity. This allowed the French physicist André Ampère to hypothesize that the magnetic properties of permanent magnets are due to the existing molecular currents within them. If an iron core is introduced into a solenoid with current, the magnetic field will sharply intensify. Why does this happen? Let's consider the following experiment. Place a coil with current into the solenoid and pass the current through this solenoid. The coil will rotate under the influence of the solenoid's magnetic field. Now, the induction vector of the current loop is directed in the same direction as the lines of induction of the solenoid's magnetic field. According to Ampère's hypothesis, the process of magnetizing the steel rod is reduced to aligning the molecular currents in the same orientation throughout the volume of the rod. In the core removed from the solenoid, the orientation of Ampère's molecular currents remains the same, so the core retains the acquired magnetic properties. Ampère's hypothesis explains why it's impossible to separate magnetic poles. When the magnet is cut, the similarly oriented molecular currents remain, and each part will again represent a magnet with two poles. The content of Ampère's hypothesis was subsequently refined in the electronic theory of the structure of atoms. But this is the theme for another video.